When the exact transformer size from a power company, or POCO, is unknown during the electrical design phase, you can follow a structured approach to ensure a safe and reliable system. The process involves estimating the peak load, determining transformer capacity, and coordinating with the POCO. For estimating the peak load, begin by calculating the maximum expected load. This calculation should use demand factors, load profiles, and include safety margins to accommodate potential future increases or unexpected loads. Demand factors account for the fact that not all electrical equipment will operate at its maximum rated power simultaneously. Load profiles illustrate how the electrical demand changes over time, reflecting variations between peak and off-peak hours. Including a safety margin provides a buffer to prevent overloading the transformer. Next, determine the required transformer capacity. Select a transformer with a capacity that is equal to or greater than the estimated peak load. When selecting the transformer size, consider factors such as voltage regulation, power factor, and the potential for future expansion. Voltage regulation refers to the transformer's ability to maintain a stable output voltage under varying load conditions. Power factor is the ratio of real power to apparent power, which affects the efficiency of the electrical system. Allowing for future expansion ensures that the transformer can accommodate increased loads without needing to be replaced prematurely. Coordinate with the POCO to obtain more accurate information about the potential transformer size and location. The POCO can provide guidance based on their existing infrastructure and the expected load characteristics of the facility. This coordination can prevent mismatches between the design and the available power supply, ensuring a smooth and efficient connection. When performing short-circuit calculations in situations where the transformer size is uncertain, several approaches can be employed to ensure safety and compliance. These approaches include making a conservative assumption, creating multiple scenarios, and coordinating with the POCO. A conservative assumption involves using the largest transformer size that the POCO could reasonably install. This approach provides a conservative estimate of the short-circuit current, which helps in selecting appropriately rated protective devices. Using a larger transformer size in calculations will result in higher available fault current, ensuring that the equipment is rated to withstand the maximum potential fault current. Alternatively, you can create multiple short-circuit calculation scenarios for different transformer sizes within a plausible range. This allows for a comprehensive analysis of potential short-circuit conditions and helps in selecting protective devices that can operate effectively under various fault current levels. This approach involves running short-circuit studies with varying transformer sizes, such as 1000 kV amps, 1500 kV amps, and 2000 kV amps, to understand the range of possible fault currents. Coordination with the POCO is crucial. They can provide data on their system impedance and potential transformer configurations, which can inform the short-circuit calculations. This data is essential for accurate modeling of the electrical system and ensuring that the protective devices are properly coordinated. The POCO system impedance, which includes the impedance of their transformers and distribution lines, affects the magnitude of the short-circuit current. Always include a safety factor in the peak load estimation and transformer capacity selection to account for any uncertainties or unforeseen increases in load. A common practice is to add an additional 25% to the estimated peak load when selecting the transformer size. This safety factor helps in preventing transformer overloading and ensures reliable operation. Conduct coordination studies to ensure that the protective devices in the electrical system, such as circuit breakers and fuses, will operate properly under various short-circuit scenarios, including those involving uncertain transformer sizes. Coordination studies involve analyzing the time current characteristics of the protective devices to ensure that they trip selectively, isolating the faulted section of the system while minimizing disruption to the rest of the facility. As new information becomes available from the POCO regarding the transformer size and characteristics, update the short-circuit calculations accordingly to maintain the accuracy and reliability of the electrical system design. Regular updates are crucial because the transformer size and impedance can significantly impact the short-circuit current levels. Accurate short-circuit calculations are essential for selecting properly rated electrical equipment and ensuring the safety of personnel in the facility. In summary, firstly, estimate the peak load by considering demand factors, load profiles, and safety margins. Secondly, determine the transformer capacity by selecting a transformer size greater than or equal to the estimated peak load, taking into account voltage regulation, power factor, and future expandability. Thirdly, coordinate with the POCO to obtain information about the potential transformer size and location. Fourthly, for short-circuit calculations, use a conservative assumption by considering the largest reasonable transformer size. Fifthly, create multiple scenarios by running short-circuit studies with different transformer sizes. Sixthly, coordinate with the POCO to obtain system impedance data. Seventhly, include a safety factor in the peak load estimation. Eighthly, conduct coordination studies to ensure proper operation of protective devices. Ninthly, regularly update calculations with new information from the POCO. By following these steps, you can effectively address the challenges of designing an electrical system when the POCO transformer size is initially unknown, ensuring a safe, reliable, and compliant installation. When calculating the maximum expected load, demand factors play a vital role in accurately estimating the actual power consumption. Demand factors are ratios that represent the proportion of the total connected load that is expected to be in operation simultaneously. These factors are typically less than 1, reflecting the fact that not all electrical equipment operates at its maximum rated power at the same time. For example, in an office building, lighting might have a demand factor of 0.8, indicating that on average, only 80% of the installed lighting will be in use at any given moment. Similarly, receptacle circuits might have a demand factor of 0.5, reflecting the intermittent use of devices plugged into those circuits. The National Electrical Code, or NEC, provides guidance on appropriate demand factors for various types of loads in different occupancies. These values are based on empirical data and industry best practices. Consulting the NEC tables, such as those in Article 220, is essential for accurate load calculations. Understanding and applying demand factors correctly is crucial for avoiding oversizing the transformer, which can lead to increased costs and reduced efficiency. An oversized transformer operates at a lower percentage of its rated capacity, resulting in higher no-load losses and lower overall efficiency. Load profiles provide a detailed view of how electrical demand changes over time. These profiles illustrate the variations in power consumption between peak and off-peak hours, as well as the impact of different types of equipment on the overall load. Creating accurate load profiles involves analyzing historical data, conducting energy audits, and using monitoring equipment to measure actual power consumption. For new facilities, load profiles can be estimated based on similar existing facilities or through simulations that model the expected operation of the electrical equipment. Load profiles are particularly useful for identifying opportunities to optimize energy usage and reduce peak demand. For example, scheduling high-demand activities, such as running large machinery, during off-peak hours can help flatten the load profile and reduce the maximum demand on the transformer. This, in turn, can allow for the selection of a smaller transformer, reducing both capital and operating costs. A safety margin is an additional capacity included in the transformer selection to account for uncertainties and potential future increases in load. This margin provides a buffer to prevent the transformer from being overloaded, which can lead to overheating, reduced lifespan, and even failure. A common practice is to add a safety margin of 25% to the estimated peak load. This means that if the calculated peak load is 800 kV, the selected transformer should have a capacity of at least 1000 kV. The appropriate safety margin depends on the specific application and the level of uncertainty in the load estimation. For facilities with a high potential for future expansion or significant fluctuations in load, a larger safety margin may be necessary. Conversely, for facilities with a stable and well-defined load, a smaller safety margin may be sufficient. When selecting a transformer, voltage regulation is a critical factor to consider. Voltage regulation refers to the transformer's ability to maintain a stable output voltage under varying load conditions. A transformer with poor voltage regulation will experience a significant drop in output voltage as the load increases, which can negatively impact the performance of sensitive electronic equipment. Voltage regulation is typically expressed as a percentage, with lower percentages indicating better performance. For example, a transformer with a voltage regulation of 3% will experience a voltage drop of no more than 3% from no load to full load conditions. The acceptable voltage regulation depends on the type of equipment being served and the sensitivity to voltage fluctuations. Sensitive electronic equipment, such as computers and medical devices, typically require a voltage regulation of 5% or less. Power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. It represents the efficiency with which electrical power is used. A power factor of 1 indicates that all the power is being used effectively, while a power factor of less than 1 indicates that some of the power is being wasted. A low power factor can result in increased current flow, higher energy losses, and reduced system capacity. It can also lead to voltage drops and instability in the electrical system. To improve power factor correction capacitors can be installed. These capacitors provide reactive power, which offsets the reactive power drawn by inductive loads such as motors and transformers. Improving the power factor can reduce energy costs, increase system capacity, and improve voltage regulation. When selecting a transformer, it is important to consider the potential for future expansion. Choosing a transformer with sufficient capacity to accommodate future load growth can avoid the need for costly transformer replacements in the future. Evaluating the long-term plans for the facility and anticipating potential increases in electrical demand is crucial. This may involve considering factors such as planned additions, new equipment installations, and changes in occupancy. Coordinating with the POCO is essential for ensuring that the selected transformer is compatible with their existing infrastructure and that the connection to the grid is properly designed. This coordination can involve discussing the expected load characteristics, the desired transformer size and location, and any specific requirements or constraints imposed by the POCO. The POCO can provide valuable information about the available capacity on their distribution system, the system impedance, and any potential upgrades that may be required to accommodate the new load. This information is crucial for ensuring a smooth and reliable connection to the grid. When performing short-circuit calculations, the conservative assumption of using the largest reasonable transformer size ensures that the protective devices are selected to withstand the maximum potential fault current. This approach provides an additional margin of safety and reduces the risk of equipment damage or failure during a short-circuit event. The largest reasonable transformer size is typically determined based on the POCO's standard transformer sizes and the available capacity on their distribution system. It is important to consult with the POCO to determine the maximum transformer size that they are likely to install. Creating multiple short-circuit calculation scenarios with different transformer sizes allows for a comprehensive analysis of potential fault current levels. This approach helps at understanding the range of possible short-circuit conditions and in selecting protective devices that can operate effectively under various fault current levels. The transformer sizes used in the scenarios should be representative of the range of potential transformer sizes that the POCO might install. This may involve considering both the smallest and largest reasonable transformer sizes, as well as intermediate sizes. By analyzing the short-circuit current levels for each scenario, it is possible to select protective devices that will provide adequate protection under all potential fault conditions. Obtaining system impedance data from the POCO is crucial for accurate short-circuit calculations. The system impedance includes the impedance of the POCO's transformers, distribution lines, and other equipment. This impedance affects the magnitude of the short-circuit current, with higher impedance resulting in lower fault currents. The POCO can provide this data in the form of a system impedance diagram or a short-circuit study report. This information is essential for accurately modeling the electrical system and ensuring that the protective devices are properly coordinated. Conducting coordination studies involves analyzing the time current characteristics of the protective devices to ensure that they trip selectively, isolating the faulted section of the system while minimizing disruption to the rest of the facility. This involves plotting the time current curves of the various protective devices on a single graph and ensuring that the curves do not overlap. The upstream protective devices should have longer tripping times than the downstream devices, allowing the downstream devices to clear the fault before the upstream devices trip. This ensures that only the faulted section of the system is isolated, while the rest of the facility remains operational. Coordination studies are essential for ensuring the reliability and safety of the electrical system. Regular updates to the transformer size and short-circuit calculations are necessary as new information becomes available from the POCO. This may involve receiving updated transformer specifications, changes in system impedance, or modifications to the distribution system. Keeping the calculations up to date ensures that the protective devices are properly coordinated and that the electrical system is operating safely and reliably. This requires establishing a process for regularly reviewing and updating the calculations whenever new information becomes available. By following these steps, you can effectively address the challenges of designing an electrical system when the POCO transformer size is initially unknown, ensuring a safe, reliable, and compliant installation. Always adhere to relevant electrical codes and standards such as the National Electrical Code, or NEC, and local amendments. Consult with qualified electrical engineers and professionals to ensure the accuracy and completeness of the electrical system design. Prioritize safety in all aspects of the design, installation, and maintenance of the electrical system.